Good morning, and welcome to Jeffrey TV, where I'm your host, Jeff Luffman, and I talk about topics that interest me, and I'm a one-man show here, setting up multiple camera angles. How you doing this morning, ChatGPT?
Hey, Jeff, I'm doing great. Thanks for asking. It's awesome to see you running your one-man show with all these camera angles and getting your content out there. How's everything going on your end this morning?
I'm working on week 2 in my data science graduate course for AI in business, DSCI 508. This is week 2, normalization, distance metrics, and clustering.
That sounds pretty exciting. Normalization, distance metrics, and clustering are some pretty foundational concepts in data science. How are you finding the coursework so far? Are you enjoying the process?
It's fascinating, and I'm using you as a tool to learn and understand.
I love that. I'm always here to help break things down, explain concepts, or even give examples if you need them. Feel free to throw any questions my way, and we can tackle these topics together. It's great that you're taking such an active approach to mastering your coursework.
Let's watch this video together.
Many of you are majoring in some form of data science. Let's think about what that means. The word science comes from the Latin scientia, which meant knowledge, knowing, expertness, or experience. A data scientist is someone with a special knowledge or expertise with data. And data, the same word here can be used as singular or plural, are facts and statistics collected together for reference or analysis. In computing, however, data is information that has been translated into a form that is efficient for movement or processing. Relative to today's computers and transmission media, data is information converted into binary digital form. If it is already converted into a digital form for us, why do we need to get so picky about what type it is? That's a reasonable question. The answer is that we want to be able to use this data to train our machine learning models, and some data cannot be added while other types can. In fact, there are 4 major classifications of data, and several sub-classifications that matter when you want to apply statistical methods to them. Nominal data is, as the name implies, in name only. Dave, Judy, Marcel are examples of nominal data. We can't add or subtract them, or say that one is twice the other. We can't even give the names any type of ordering. Ordinal data contains an implied order. Good, better, best suggests order just as first, second, and third do, or cold, warm, hot. They all have an order that's implied there. Interval data is numeric, but it's not absolute. I'll explain that in a moment. You can add and subtract interval numbers, but not divide one by another and get meaning. Temperature is often expressed in degrees Fahrenheit or degrees Celsius, and as such it represents interval data. You can say that 90 degrees Fahrenheit is 10 degrees warmer than 80 degrees Fahrenheit, but you can't say, or at least can't truthfully say, that 100 degrees Fahrenheit is twice as hot as 50 degrees Fahrenheit. Ratio data has numbers on some absolute scale. If I have 2 apples and you have 6 apples, we can not only say that you have 4 more than I do, but also that you have 3 times as many as I do. Note that some types of data can be one classification in some instances and another classification in others. Let's rethink the idea of temperature. We said that 100 degrees Fahrenheit is interval data because it's not twice as hot as 50 degrees Fahrenheit. However, if we were to express temperature with an absolute scale, such as degrees Kelvin or degrees Rankine, then it becomes ratio data because 100 degrees Kelvin does have twice as much heat as 50 degrees Kelvin. On the Kelvin scale, which we get by adding about 273 to the Celsius scale, 0 degrees Kelvin is absolute zero. That's the temperature where atoms stop moving and the heat is 0. So temperature can be interval or ratio, but it can also be ordinal. We can say that today is hotter than yesterday and perhaps rank the days as the coldest or hottest of the month. Warm, hot, hotter, hottest as an ordinal ranking. Finally, temperature can also be nominal. Yesterday was uncomfortable, but today feels fine. We don't know if yesterday was uncomfortable because it was hotter or colder, so it's not ordinal, it is nominal data. Note also that just because we used 4 classifications for data does not mean that these 4 are all you need to know. You have to analyze numerical data differently than categorical data, otherwise it would result in a wrong analysis. But even if you determine your data is numerical and interval, it could also be discrete or continuous, and computing something as simple as a mode or median will be a little different for them. Knowing the types of data you are dealing with helps you to choose the correct method of analysis.
Okay. So, what do you think, chat?
That was a great breakdown of the different types of data. It's always fascinating to see how understanding the classification of data can shape the way we analyze it. I think it's really helpful, especially in the context of machine learning and AI, to get those distinctions right so you can apply the correct methods. What do you think? Does that help clarify some of the concepts you're working on?
I feel like I've had this particular block of instruction over this specific information in my academic career about 900 times. And I feel like every single time that I see it, I have to relearn it and take a moment to understand it again. So if we have a group of 30 students in a class, and we could break those students down nominally by their gender, correct?
Exactly. If you're breaking the students down by gender, that's a great example of using nominal data, because you're categorizing them by a label without any sort of inherent order. It's totally normal to feel like these concepts need a little refreshing each time you come across them, especially when you're applying them in different contexts. It's all part of the learning process.
All right, so if we have 30 students in our class, we can rank them in order. That would be ordinal data. We can rank them by their age. And
exactly. Ranking them by something like age would definitely be ordinal data, especially if we just place them in order without focusing on the exact difference in their ages. If we start looking at the exact age difference, like saying one student is 2 years older than another, then we start moving into interval or ratio data. But just ranking them from youngest to oldest is a perfect example of ordinal data. You're definitely getting an A.
So, please expand on your example of using the class for interval data.
Sure, if we take the same class of 30 students and look at something like their ages in years, we can treat that as interval data. For instance, if one student is 15 years old and another is 17, you could say there's a 2-year difference between them. With interval data, we can talk about the differences between values in a meaningful way, but there's no true 0 point. For example, someone being 0 years old isn't really meaningful in the same way that 0 degrees Celsius isn't an absolute 0. So using a class for interval data would be all about measuring those differences in a way that makes sense, even if we're not dealing with a true 0 point. Let me know if that helps clarify things.
Absolutely. And if we were going to take our ratio data, it wouldn't necessarily apply to our class of 30 students, would it?
That's a great observation. Ratio data typically involves a true 0 point and allows for meaningful multiplication and division. For example, if we were looking at something like test scores expressed as percentages, that could be considered ratio data, because a score of 0% means no correct answers, and a score of 100% means a perfect score, and you can meaningfully say one score is twice another. In the context of our class, we might not always find a perfect ratio example unless we're dealing with something that has a true 0 and can be compared proportionally. So it really depends on the kind of data we have, but you're right that not all data from a class setting will fit neatly into the ratio category.
Let's read this next Science Magazine article from 1946, authored by S.S. Stevens, titled "On the Theory of Scales of Measurement."
That sounds like a fascinating read. S.S. Stevens' work on the theory of scales of measurement is actually foundational in how we think about data types today. Nominal, ordinal, interval, and ratio scales all come from his... No worries at all. Whenever you're ready, we can explore that article or any other topic that interests you. Just let me know how I can help or what you'd like to dive into next.
So S.S. Stevens is like the father of data science?
In a way, you could say that S.S. Stevens laid some of the groundwork for how we understand and classify data, which is definitely a huge contribution to fields like data science, statistics, and psychology. His work on the theory of scales of measurement really helped shape the way we think about data and the different ways we can measure and analyze it. So while he might not be the sole father of data science, he certainly is one of the key figures whose work continues to influence the field today.
Who is the sole father?
Data science is such a broad and interdisciplinary field that it's hard to attribute it to just one father. It's really a combination of contributions from many fields, including statistics, computer science, mathematics, and domain-specific knowledge. That said, there are a few key figures who are often recognized for their foundational contributions. For example, John Tukey, a statistician, is credited with coining the term data analysis and had a huge influence on modern exploratory data analysis techniques. And then you have people like Claude Shannon, who laid the groundwork for information theory, and even more modern figures in machine learning and AI like Geoffrey Hinton or Andrew Ng. So it's definitely a team effort across decades and disciplines.
Nice.
I'm glad you found that helpful. It's always interesting to see how many brilliant minds have contributed to what we now call data science. If there's anything else you're curious about, or if you want to dive into another topic, just let me know.
Testing your capabilities right now, are you able to understand the text that's on the screen?
I can see what's on the screen, so if you need help with something specific, or if there's text you'd like me to take a look at, feel free to let me know.
I don't have my glasses. Can you read this to me?
Of course, I'd be happy to help. Just let me know what's on the screen that you'd like me to read, and I'll do that for you.
Can you read the first paragraph, please?
Absolutely. Just go ahead and show me the paragraph you'd like me to read, and I'll read it out for you.
Starting right here and highlighted in blue.
Got it. I don't see the specific paragraph highlighted in blue from my end, but if you read out a few words or give me a bit of context, I can definitely help from there.
It says, for 7 years, a committee of the British Association for the Advancement of Science debated the problem of measurement. Appointed in 1932 to represent Section A, Mathematical and Physical Sciences, and Section J, Psychology, the committee was instructed to consider and report upon the possibility of quantitative estimates of sensory events. Meaning simply, is it possible to measure human sensation? Deliberation led only to disagreement, mainly about what is meant by the term measurement. An interim report in 1938 found one member complaining that his colleagues came out by that same door as they went in, and in order to have another try at agreement, the committee begged to be continued for another year.
Thanks for sharing that. It's fascinating to see how long the debate around measurement and the definition of measurement has been going on. The story about the committee from the British Association for the Advancement of Science really highlights how complex and nuanced the idea of measuring human sensation and perception can be. It's a reminder of how foundational these discussions have been to fields like psychology, data science, and beyond.
I see here the table 1 illustration that lays out the scale, the base, empirical operations, mathematical group structure, and permissible statistics, invariative. nominal, ordinal, interval, and ratio.
Yes, that table is a classic reference from Stephen's work on scales of measurement. It really breaks down how different types of data, nominal, ordinal, interval, and ratio, are treated differently in terms of what kinds of mathematical operations you can perform on them and what statistical methods are appropriate. It's such a foundational concept that continues to influence how we approach data analysis today. It's really cool that you're diving into this. It gives such a solid foundation for understanding the nuances of data in your coursework.
Yeah, it is really cool.
Absolutely. It's always exciting to dive into these foundational concepts and see how they connect to the bigger picture, especially in fields like data science and AI. If you ever want to explore more, or if there's anything else you're curious about, I'm here to help. Keep up the great work.
Yeah, I'm gonna save that. So I can come back to it.
That's a great idea.
The data classes.
Absolutely. Keeping these concepts handy will definitely help reinforce your understanding as you go forward in your coursework. And if you ever want to revisit them or dive deeper into any specific topic, I'm always here to help. Just let me know whenever you need a refresher.
Wow, look at this scale that's already in my coursework.
That's awesome. It's always cool when you can directly connect what you're learning in your coursework to these fundamental concepts. It really shows how relevant and foundational they are. If you have any questions about how it ties into what you're studying, or if you want to explore it further, I'm here for it. Keep up the great work with diving into your materials.
This portion states, as Jeff Heaton states in the next text, you can usually determine the type of observation by observing what operators are valid on it. Take gender, for example. Can you add, subtract, multiply, or divide two genders? No. However, you can say the gender for person A is the same as the gender for person B. What type of data? Nominal data. Good, better, best implies ordinal. There's a ranking. What temperature is far as nominal, ordinal, interval, ratio? Temperature is, let's say, it's got a ranking. So,
that's a really
ordinal, am I right?
Absolutely. When we talk about temperature in terms of hotter or colder, we're definitely looking at it in an ordinal sense because we're ranking it without necessarily measuring the exact difference. And then if we think about temperature in degrees Celsius or Fahrenheit, we're usually talking about interval data because there's no true 0 point. But if we switch to an absolute scale like Kelvin, then it becomes ratio data. So it's cool to see how the type of data can shift depending on how we measure and talk about it.
So good, better, best is the same as hot, hotter, hottest?
Exactly, you got it.
Cool.
Both good, better, best, and hot, hotter, hottest are great examples of ordinal data. They both represent a ranking or an order, but they don't measure the exact difference between each level. It's all about the relative position rather than precise numerical differences, and that's what makes it ordinal.
Okay. You can see that the next portion that we are working on is the Euclidean distance.
Oh, that's a fun topic. Euclidean distance is essentially the straight line distance between 2 points in a multidimensional space, kind of like measuring the shortest path between 2 points on a graph. It's super useful in clustering and many machine learning algorithms. It's great that you're diving into that next. If you have any questions or need help with examples, I'm here to help.
Euclidean formula for the hypotenuse of a right triangle. So that's c squared equals a squared plus b squared.
Exactly. That's the Pythagorean theorem, which is the foundation of Euclidean distance in 2 dimensions. When you're finding the Euclidean distance between 2 points, you're basically extending that same idea into multiple dimensions. In 2 dimensions, the distance between 2 points, say x1, y1, and x2, y2, is the square root of the sum of the square differences between their coordinates. It's like applying the Pythagorean theorem in any number of dimensions. It's such a fundamental concept that underpins a lot of what you do in data science, especially in clustering and other algorithms that rely on distance calculations.
That's fascinating.
I'm glad you think so. It's always fun to see how these fundamental
When we talk about distance, the most common
watch
type
this
of
video.
distance is the Euclidean distance. And it's easy to visualize the Euclidean distance in 2 dimensions. It becomes the hypotenuse of the familiar right triangle. Let's say we want the distance between point A and point B. If we subtract the x values and then square them, and then subtract the y values and square them, the sum is going to give us the square of the hypotenuse. In this case, that's 4 plus 4 equals 8. Distance here squared, and this distance here squared. And then we take the square root of that, and we get 2.828, and that's our distance between A and B. Likewise, the distance from between points B and C, and A and C, can be found the same way. In 2 dimensions, this is easy to calculate and easy to visualize. Now, all of us had learned that Euclidean formula for the hypotenuse of a right triangle. C squared equals A squared plus B squared, and this is easily extendable to multiple dimensions. Once we go beyond 2 or 3 dimensions, though, visualizations can be misleading. An anamorphism is a distorted projection or perspective, especially an image distorted in such a way that it becomes visible only when viewed in a special manner. When we look up at the winter sky at night, we see the constellation Orion, the mighty hunter. From our perspective, it looks like Bellatrix here is close, very close, to Mysa. But in reality, we are 4 times closer to Bellatrix than Bellatrix is to Mysa. Those who believe in astrology have a very Earth-centered perspective. Euclidean distance is easily extended mathematically, but not visually, to any number of dimensions. Essentially, just assume your observations are based on 11 variables, such as height, weight, eye color, gender, age, income, level, country of origin, years of education, number of fluent languages, favorite sport, and political affiliation. How can we calculate the Euclidean distance in higher dimensions? Actually, pretty easily. We use the same process. On point 1 to point 2, we can say 1 minus 2 squared plus 3 minus 3 squared plus 0 minus 5 squared plus 2 minus 0 squared plus 4 minus 8 squared and 7 minus a minus 3 squared and negative 2 minus 1 squared, 0 minus 1 squared, negative 3 minus a negative 2 squared, 5 plus 5 squared, and 8 minus 7 squared, all come out to the square root of these differences. 1 plus 0 plus 25, on like that. And that square root is 12.57. So even though we can't wrap our heads around the visualization of what this 11-dimensional space is like, we can say with certainty that the distance between these 2 points is 12.57. Again, it's easy to visualize in 1, 2, or sometimes 3 dimensions, but you get into 4, 5, and beyond, and it's hard to see this, but mathematically, it's a pretty easy process.
Fascinating.
It really is. It's amazing how mathematics lets us work in these higher dimensions, even when we can't visualize them. The fact that we can calculate the distance between points in an 11-dimensional space just as easily as we do in 2 dimensions is pretty mind-blowing. It definitely shows the power of mathematical abstraction and why these concepts are so important in data science and AI. It's awesome that you're diving into all of this.
Discuss anamorphism.
Anamorphism is a really interesting concept. In the context of that example about constellations in the night sky, it refers to how our perspective can distort our understanding of spatial relationships. When we look at constellations, we see patterns that look flat, but in reality, the stars are at vastly different distances from us. It's a great analogy for how certain mathematical or spatial relationships can be clear in one context and distorted in another. In higher dimensions, we rely on mathematical principles rather than visual intuition to understand relationships, just like how the true distances between stars in a constellation are understood through measurement rather than what we see. It's a pretty fascinating concept.
Indeed. Let's discuss Manhattan distance as it relates to taxi cabs. Probably Uber nowadays.
Absolutely. Manhattan distance, also known as the taxi cab distance, is a way of measuring distance that reflects how you would navigate a grid-like path. Like the streets of Manhattan, instead of measuring a straight line between 2 points, it sums up the absolute differences along each dimension. So if you were moving through a city grid, you'd count the blocks you travel along the streets and avenues. It's a really practical way to...
Manhattan or taxi cab distance is another reasonably common metric for distances. And there you would say that I can't take the hypotenuse here because I have to travel along the streets. I can't drive through the buildings. And so I'd have to add up all these separate pieces, kind of a stair-step approach.
Exactly. That's a perfect way to put it. The Manhattan distance really does capture that idea of having to move along a grid, turning corners rather than cutting diagonally through buildings. It's a great analogy for certain real-world scenarios, and it's super useful in fields like urban planning, logistics, and even certain machine learning algorithms where that grid-like structure matters. It's fascinating how different distance metrics can give us different insights depending on the problem we're trying to solve.
Let's move to clustering distance rules.
In order for the algorithms to work, there are 4 distance rules that we have to specify. The distance cannot be negative, so the distance from I to j has to be greater than 0 whenever j is not equal to I. The distance from any cluster to itself has to be 0. The distance from I to I is equal to 0. And the distance has to be symmetric. That means going from I to j, you get the same distance that you would get from j to I. Now that sounds intuitive, but in some geometries, that's not necessarily the case. Picture yourself in a large metropolitan area, going from one house to another house, maybe only 300 feet down the street, but it's a one-way street. In one case, that'll be about 300 feet. In the other case, it'll be much longer than that because you'd have to at least go around the entire block to be able to get to the other house. So distance being symmetric is important here. And also that a triangular inequality holds. And that's just basically saying that if you have 2 points and you get the distance between those and you add the distance from that second point to a third point, that's going to be greater than or equal to the distance if you jump directly from that first point to the third point. Now, given these rules, we can choose any number of different metrics for distance. And here's a table of common distance measures. Note that the second one is essentially the first one, except you don't have to take the square root. If all you care about is whether point A is closer to point B or to point C, why bother to take the square root? It's just extra calculations.
Good point, Dave. Good point. So, I'm feeling like this is important, complex information, Chad.
It definitely is important and can feel complex, but you're doing great with it. Understanding these distance metrics and the rules around them, like symmetry and the triangular inequality, really helps form the foundation for a lot of clustering algorithms and other machine learning techniques. It might take a little time to get fully comfortable with all of it, but you're definitely on the right track, and I'm here to help whenever you need a hand with it.
Let's discuss normalizing data.
Many of you will be taking a database course, and in that you will encounter Dr. Codd's 12 steps for normalization of a database. And this has nothing to do with normalization as we are using the terms. So keep in mind that in a relational database, data is normalized to reduce redundancies, and that's not the application or meaning that we have for normalization. Our sense of normalization is to keep one parameter or one feature from completely overwhelming another one just from the sheer differences in size. For example, Zillow must normalize their data. And if they didn't do that, then the price as a function of square footage would overwhelm location and number of rooms. If you had a 3,000 square foot house, it would appear to sell for twice as much, say, as a 1,500 square foot house. But maybe the number of bathrooms was really important to you. In order to have the bathrooms start out on equal footing with the square footage, you have to normalize that data. What are some examples of that? Well, we have income versus height. Robert Wadlow in Alton, Illinois was 8 feet, 11.1 inches, and was considered the tallest human on the planet, whereas Chandra Dangi of Nepal was declared the shortest human at 21.5 inches. Now compare that range to, say, the income range from homeless folks or those in bankruptcy to Jeff Bezos, our first centibillionaire. So depending on the data, you may have to normalize that in the method that you use. The names that we give here are a guide to help us normalize more effectively. There are many ways to normalize, and classifications may not be absolute. Zip codes might be nominal, as suggested in the text, or they might be ordinal if we're talking about relative cost locations. Again, if I pick Alton, Illinois, that'll be 62002. Relatively modest housing costs there. But if we took 90210, Beverly Hills, the housing is going to be a lot more costly there. So we might say that 90210 is a more expensive zip code to be in than 62002. Temperature can be an interval when you check the weather forecast. You might say it's 50 degrees or it's 75 degrees Fahrenheit, or it might be a ratio if you're a researcher in a cryogenics laboratory experiment. You're working with the Kelvin temperatures, and you say that I lowered this material down to 100 degrees Kelvin, very cold, and it exhibited totally different characteristics when I lowered it further down to 50 degrees Kelvin, which essentially would be twice as cold. Temperature could also be ordinal and classified as cold, warm, hot. Very hot. Boy, it's so hot.
So hot. Hotter.
If you say that yesterday the temperature was uncomfortable, but today it's quite comfortable, that doesn't tell me whether yesterday was uncomfortable because it was hotter or yesterday was cooler. We just know that it wasn't as nice as it was today. Quantitative observations. Box and whisker plots and violin plots often are helpful in the analysis of raw data and the choice of how to normalize it. In your textbook, Jeff Heaton talks about the equilateral method of categorizing, say, colors, or taking observations that are not numeric there. And in theory, that seems like it would save a little because you've got one less dimension. Now you're using n-1 instead of the full n. Subsequent to that textbook being published, though, he came up with an article that says it really doesn't help very much, and it complicates some of the calculations on various different techniques. So it's usually better to use the 1 of n rather than the 1 of n-1. It's a lot easier for most of the algorithms to handle. And if you do want to keep order, good, better, best, then you might want to assign the n categories numbers from 0 to n-1, or some consistent number. It doesn't have to be like that, and you might even have to have a weighting on there. It might be 1, 5, and 6, depending on your ordinal observations. Maybe it's very cold, and hot. There might be a bigger gap between cold and hot than there would be between very cold and cold. Some people are not comfortable at first with the idea of extending the dimensions and how those would affect your calculations. So let's go through an example here. Let's say that we have those 11 variables, height in inches, weight in pounds, eye color. In the eye color, we're working with 4 different possibilities: brown, blue, green, or some other color. Gender, we'll say male or female or other. Age will be in years. Income level will be in dollars per year. We'll just pick some geographic areas: North America, South America, Europe, Asia, Africa, and Australia. Years of education, number of fluent languages, a favorite sport, and on here we're just saying the sports could be baseball, hockey, chess. St. Louis is the big chess center. A political affiliation. And what we're doing when we do that, when we turn these into 1 of n, is we're increasing the dimensions to 28 from 11. So where gender was 1 dimension before, it became 3. Where eye color was 1 dimension before, it became 4 dimensions. And so now when we represent these things, we would say that in this case, maybe height was 72 inches and weight was 203 pounds. Well, the eye color would mean we have a 0 for brown here. We have a blue. So if the eye color was blue, these 4 dimensions here would be 0, 1, 0, 0. If the gender were male, we would say female gets a 0, male gets a 1, other gets a 0. Age would be in there as normal. Income level is normal. The next one to be expanded would be origin from the 7 different possibilities, and this person happens to be from North America. So only North America will have a value. All these other dimensions will have zeros. And we do the same approach for the rest of these. Now, when we're taking the distance now from point 1 to point 2, all we do is the same subtractions that we did before. 72 minus 65 squared, the 203 minus 128 squared, the 0 minus 1 squared, 1 minus 0 squared, 0 minus 0 squared, on like that. It's exactly the same process. And just as a reminder, the reason that we're squaring all these terms is that we don't want positives and negatives to cancel each other out. So now we've done this, and we've come up with a value, the square root of this value, but what's wrong with this approach? What have we forgotten to do here? Well, in this case, look at the income. 70,000 minus 95,000, and then we square that difference. So 25,000 squared is going to be 625 million. Whereas gender over here at most is going to contribute a very small number. So that means that height, weight, income level, years of education, and number of fluent languages should be normalized here to values from 0 to 1. Otherwise, they're going to overwhelm the other potential factors in here. And in this case, we see that the income level is going to overwhelm everything. So to prevent that, we definitely want to normalize these values. Here's some free references for Python. One is Automate the Boring Stuff with Python by Al Swigart. I think his books are excellent. And even though this is for sale on the website and on Amazon, he also gives a free version out on the website, so you can read it for free there. It has a lot of great material for the people who are coming to Python maybe as their first language. Now, if you're already experienced with another language, say C or Java or C# or R, and you just want to say, okay, how do I get up to speed really quickly? I don't want to have to read a whole lot of extra stuff. Just show me the syntax differences and how I would get going on this. Then I recommend A Whirlwind Tour of Python by Jake Vanderplas, and this is also free on the internet. So two great resources for you, one better than the other depending on where you're coming from in your level of expertise with programming.
All right, that's exciting.
Absolutely. It really is. Diving into normalization and understanding how to balance different features in your data is such an important step in data science. And it's awesome that there are so many great resources out there to help you along the way, whether you're new to Python or just looking to level up your skills. Keep that excitement going. You're doing great.
Just checking out the O'Reilly page here. There it is. Python Crash Course.
That's another fantastic resource. The Python Crash Course is a great way to quickly get up to speed and build a solid foundation in Python. It's perfect for diving into data science projects and understanding the fundamentals of coding. It's great to see you exploring all these resources and building up your toolkit.
ChatGPT has a feature for scheduling now, right?
I don't have a built-in feature for scheduling tasks or setting appointments directly, but I can definitely help you with tips on how to manage your time, recommend scheduling tools, or even help you plan out your tasks. Just let me know what you need, and I'm here to help.
Let's talk about observation types.
Sure. When we talk about observation types, especially in the context of data science, we often refer to the different ways data can be categorized or measured. These types include nominal data. This type of data represents categories or names without any inherent order. Examples include gender, eye color, or types of cuisine. You can't really rank nominal data. It's just about labeling. Ordinal data, this type has a meaningful order or ranking, but doesn't necessarily have equal intervals between the ranks. Examples include survey ratings like satisfied, neutral, and dissatisfied, or educational levels like beginner, intermediate, and advanced. Interval data, this type of data has meaningful intervals between values, but no true 0 point. A classic example is temperature in Celsius or Fahrenheit, where the 0 point is arbitrary and not an absence of temperature. Ratio data, this type has all the properties of interval data, but it also includes a true 0 point, meaning that 0 indicates the absence of the quantity being measured. Examples include height, weight, and income, where you can say one value is meaningfully twice or half another value. Understanding these different types helps in choosing the right statistical methods and ensures that the data is analyzed correctly. If you want to dive deeper into any of these, just let me know.
Discuss normalized data observation item.
When we talk about normalized data, we're typically referring to the process of scaling data so that it falls within a specific range, often between 0 and 1. This process helps ensure that no single feature or variable dominates the analysis simply because it has larger values. For example, if you're analyzing data that includes both income, which could be in the tens of thousands, and age, which is usually a smaller number, normalizing the data ensures that each feature contributes equally to the analysis. This is especially important in machine learning algorithms like clustering or neural networks, where the scale of the data can significantly impact performance. Normalization helps create a level playing field for all the variables and leads to more accurate and meaningful results. Let me know if you'd like to explore this further.
Discuss the relationship to z-scores.
Absolutely. Z-scores are a specific way to normalize data by transforming it so that it has a mean of 0 and a standard deviation of 1. When you calculate a z-score, you're essentially measuring how far away a particular data point is from the mean of the data set in terms of standard deviations. This is really useful when you want to compare data points from different distributions or when you need to identify outliers. By converting everything into z-scores, you're effectively normalizing the data in a way that allows for direct comparison. It's a powerful tool in statistics and data analysis, helping to standardize different types of data for meaningful insights.
Adding to the apparent number of dimensions.
When we talk about adding to the apparent number of dimensions, especially in the context of data normalization or feature engineering, it usually refers to the process of transforming categorical variables into multiple numerical features. One common method is one-hot encoding, where each category of categorical variable is turned into a separate binary column. This process effectively increases the number of dimensions in your data set because you're adding new features. This helps machine learning algorithms understand and use categorical data more effectively. It does increase the dimensionality, which can sometimes lead to challenges like the curse of dimensionality, but it also ensures that each category is represented in a way that algorithms can interpret correctly. If you'd like to dive deeper into this topic or have any specific questions, just let me know.
For example, in the previous video, we discussed how the dimension of salary could result in a number that's far greater than gender.
Exactly. When you're working with data that includes features with vastly different scales, like salary and gender, the numbers can be on completely different orders of magnitude. For example, salary might be in the tens of thousands or even higher, while gender is typically represented as a categorical that gets encoded into a small range of values, like 0 and 1. Without normalization, the larger numbers, such as salary, can dominate the analysis and overshadow the impact of other features.
Clustering is really cool, since unlike most machine learning methods, you do not have to have any pre-labeled data. It's one of the main techniques in the category of unsupervised machine learning algorithms. But it's not magic. It might be the case that no reasonable clustering can be done. Picture a situation where you have a bucket of white sand and another of brown sand, and you mix them both up in a shaker. It might be nearly impossible to separate the two colors again. Real data is sometimes very messy. In some cases, we have to spend a long time cleansing the data before we can employ our fancy techniques on it. Now, a common complaint among data scientists is that 80% of their time is spent collecting and cleaning the data, that is to say, making it tidy. Of course, then at the other end, we also say that the last 80% is spent presenting your results in a manner understandable to other people. The point here is that running the model is often a small percentage of the time of data science. Clustering can sometimes be thought of as similar to the children's show Sesame Street, where they sing, "One of these things is not like the others. One of these things doesn't belong. Can you tell which thing is not like the others by the time I finish my song?" In most real-world cases, the complexity is high. Optimization may not be feasible, but a decent approximation might be obtainable. Let's consider a data set of points. We assume that it's possible to find some criterion, not unique, so that each sample can be associated with a specific group. Conventionally, each group is called a cluster, and the process of finding the function, this function g of x, is called clustering. Right now, we are not imposing any restriction on the clusters. However, as our approach is unsupervised, there should be a similarity criterion to join some elements and separate other ones. Different clustering algorithms are based on alternative strategies to solve this problem, and they can yield very different results. Now here's a real-world example that's unfortunately not being used yet in the industry. The body mass index limits, or BMI, were set more than 100 years ago. They were based on medical opinions at that time. If calculated today using clustering techniques, the results would be much different, especially if combined with other features such as age and activity. One problem with the BMI approach is that many professional athletes are rated as overweight because they have more muscle mass. Seniors have low BMI are actually more risky than their slightly overweight counterparts because they may not have enough reserve fat to sustain a flu in winter. When you really think about it, the world is not as nice and crisp as we assume in a lot of our algorithms. It is pretty fuzzy. I have a couple of readings that go into detail on this that are part of the assignment. When you have a physical exam, a body mass index of 30 or higher characterizes you as obese, while a body mass index of 29 is just considered overweight. A person with a BMI of 30.000 probably is not that much more of a weight risk as a person with a BMI of 29.999. The world is very fuzzy, and there's much overlap. At the airport, clustering techniques are used as a part of the TSA screening for terrorists. It's a simple technique in both concept and implementation, but it has many valuable applications.
All right, chat. Well, that's where we're gonna take a pause today. That's a good place to take a pause, don't you agree?
Absolutely, that's a perfect spot to pause. We covered a lot of ground, and it's always good to let all that information sink in. Clustering and the different ways we measure and analyze data are fascinating topics, and you're doing a great job exploring them. We can pick up right where we left off whenever you're ready to dive back in. Just let me know.
Sounds good.
I'm glad you think so.